Good morning, student. In continuation of my previous lecture, which was based on the series of statistical thermodynamics, today I am going to deliver the last topic of this series, that is Fermi Dirac statistics. Dear students, I hope that you have gone through my two previous lectures. One is Maxwell-Boltzmann statistics and second is Bose-Einstein statistics. And I have already discussed to you that if you understand the Maxwell-Boltzmann statistics and Bose-Einstein statistics, it will be very easy for you to understand this Fermi-Dirac statistics, because in your course content you have to study all the three and ultimately you have to compare and what are the important characteristics of these three statistics. As you know that Fermi-Dirac statistics is very similar to the Bose-Einstein statistics, but there are certain differences. In Maxwell-Boltzmann statistics, generally we consider the particles are distinguishable, but in Bose-Einstein's particles are indistinguishable, but there is no restriction for the occupancy. But here you will see that there is a restriction and we have to follow the most important concept, the Pauli exclusion principle. And like Bose-Einstein statistics, the Fermi-Dirac statistics is also very important in physics as well as in chemistry, because most of the research related to the astrophysics, research related to the nuclear physics, research related to semiconductor, superconductivity, atomic structure is based on such type of Fermi-Dirac statistics, as well as of course nowadays material science is also useful if you understand the Fermi-Dirac statistics. And I hope that you have already referred most of the very good physical chemistry books for the derivation of all these statistics. And similarly, I have also referred some of the good books like Statistical Mechanics, McCaury, M.Sc. Gupta, Statistical Thermodynamics, and as well as the Statistical Thermodynamics by Tan and Lienhardt. And of course, I also referred the Physical Chemistry by G.M. Barrow, Physical Chemistry by Levine, and other things. Now, as you know that whenever I start any topic, I always give some very elementary information about the history of that concept. And you know, like Bose-Einstein statistics was developed by great scientist S.N. Bose and of course Einstein. Similarly, name itself is a definition, Fermi-Dirac. One Fermi, Enrico Fermi is from Italy, Italian scientist, and Paul M. Dirac from UK, Cambridge. And they actually developed the statistics independently and they have published separate paper. And for the knowledge of the student, I am very glad to inform you that both the scientists are Nobel laureate. Both the scientists are Nobel laureate. Fermi was awarded Nobel Prize in 1938 of course, for the induced radioactivity. And similarly, Paul Dirac was awarded Nobel Prize in Physics for the atomic theory, and he was awarded this Nobel Prize with this great scientist Schrodinger, like that. So that is the story, and if you see the literature, you will get the original research papers of both Fermi and Dirac, and I am really grateful to the website and Google. From that I have collected these original research papers of Dirac, St. John College, Cambridge, and the article published in Proceedings of Royal Society of the Chemistry 1926. So therefore, you always refer that the Fermi-Dirac statistics was developed because first time this paper was published, and this is the original paper, and I have collected from the internet like source, and this is a big paper, and of course I will derive all the things, but you see this is the 1926, today is 2026, that is we are celebrating 100 years of Fermi-Dirac statistics. And if you see the final derivation, I will of course discuss with you. Of course, the notation may be different, but the system will be same. So this is the first paper of this Dirac. Similarly, that Fermi is also published a series of papers. Of course, he also published in paper 1923 also, then 1927, but in 1926 he also published paper, of course, in different languages, and I have taken this paper from this Springer nature link, indistinguishable elements in the origins of quantum statistics. Now, so that you must know the importance of the things, that now we are living in the digital age, so everything is available in this website. So this is nothing new, but just for the knowledge of information, I am just sharing this, because I am really grateful to the website. Now coming to the first point, that this is also my style, that whenever I derive any equation, I must give the final equation of that equation. And if you see very carefully, that whether it is a Maxwell-Boltzmann or Bose-Einstein or Fermi-Dirac, almost very similar. And here I am giving two forms. One is the, actually we are doing nothing, just the occupancy of the electrons, different energy levels. So it is the probability distribution, or sometimes it is called the Fermi distribution, that a state with energy is occupied. But if you see that, I just want to use the pen. I just give your information. Generally, we write, if it is a Maxwell-Boltzmann, so Ni equal to Gi, the statistical weight factor, exponential alpha plus beta, like that. Beta. This is a general equation. Or even I can write Ni by Gi is 1 divided by, and it is Maxwell-Boltzmann. And if I substitute the value of alpha is negligible there, so this is exponential, and Ei, you know that beta is equal to 1 by kBt, with the Boltzmann constant. Now, if it is a Bose-Einstein, so it is like here I can write -1. But here you see, same thing we have written here, that you know the values of beta, 1 divided by kBt, which is Boltzmann constant, you all know, 1.38 into 10 to the -22 joule per mole. And if it is the alpha, is the chemical potential, which is temperature dependent thing. And of course, so if I substitute the value here, so I will get exponential EI minus chemical potential, then this is actually KBT plus 1. But you know that if the temperature is, of course, 0 Kelvin, absolute 0 degree centigrade, that chemical potential can be written as Fermi energy. I can write E or equivalent F, Fermi energy. Finally I will discuss the importance of that equation. What is Fermi level and the Fermi energy, which is very important. And of course, in terms of number of particles, statistical weight factor 1 divided by exponential alpha, or even I can write exponential alpha plus beta EI plus 1. In Ghosh-Einstein is minus 1, and in normal Maxwell distribution. So this is the final equation. Now coming to the derivation. So for examination point of view, what we do, first we write the postulates. Now, one of the most important difference between Ghosh-Einstein and Fermi-Dirac is that here, generally we take the particles like electrons, protons, neutrons, positrons like that. But yes, particles are non-interacting, identical, indistinguishable. But above all, most important point is that all the particles follow another very important concept, that is called the Pauli exclusion principle. And I think you have already studied in your B.Sc classes. And again I must tell you that Pauli was also awarded Nobel Prize in Physics for the Pauli exclusion principle in 1925. And they derived in 1926. And the most important concept is that no two electrons in an atom can have the same quantum state. Or simply, we can call it that, suppose there are 4 boxes or 5 boxes or 6 boxes, different statistical weight factors, only one particle is allowed. Whereas in Bose-Einstein, there is no restriction. So this is the most important example. So therefore, I am just giving the top priority. Particles are indistinguishable. Let me repeat: non-interacting, identical, following the Pauli exclusion principle. Second, I have already told you that Maxwell-Boltzmann is the classical mechanics, but it is an example of quantum statistics, because we will consider the spin, we will consider the wave function, symmetric or antisymmetric. I'll just explain here. So don't forget that there is a concept of the Pauli exclusion principle. Now other postulates is that the particles obeying the Fermi-Dirac statistic, electrons, positrons, protons, neutrons, neutrinos, helium-3. You must know that what are the different particles. Now first postulate I have already told you that an example of the quantum statistics, Pauli exclusion principle, no two fermions. Another thing is that, like in Bose-Einstein, we referred as a boson. So in future derivation, I will use electrons or particles are fermions. And in that part, there is a integer, but in Fermi-Dirac, half integer, half, 3/2, and 5/2 like that. But another important thing is that it will follow the anti-symmetric wave function. Suppose there are 2 particles and wave function is mu1 or 2 and distance is r1 and r2. So when there is the interchange, there is a change in sign. So that is called the anti-symmetric wave function. Whereas in Bose-Einstein, that is the symmetric wave function. I can give you the example. This is the two fermions position is r1 and r2 because particles are indistinguishable. I will explain that how we can study this thing. So when there is a swapping or interchange, sign r1 and r2 is anti-symmetric, it is minus sign r2 with an r1. So in scientific language, you can call that the wave function of a system of multiple particles or two fermions may be different. The large number of GI may be very high as compared to number of particles, the quantum states, and there is change in sign. And I have already discussed the micro state and the macro state, different energy levels, suppose E1, E2, E3, E4, E5 like that, K, L, M, N, and then different quantum states, G1, G2, G3, G4 like that. So another condition is, so you have to write the postulates. Now we start the derivation. Again, I just repeat for the student that first there are only 3 steps. First, the postulate characteristic. Second, how many different ways. So therefore, it is statistics, probability distribution, and you have to calculate the most probable distribution. You have to use the combinatorial rules, different types of combination, permutation and the combination. And it is up to you. Here I am just using capital N. In some of the books it is written small ni, number of particles. You don't worry for that. And for statistical weight factor I am just using GI. But the condition is that the value of GI must be greater than the N. So now postulates is over. Now the steps. Again it is very similar to your Maxwell-Boltzmann as well as the Bose-Einstein. We will use the constraint, rules of conservation of the particles, conservation of the energy is fixed or constant, and then we use the probability, use Stirling approximation, get the maximum value, and then use the Lagrange's method of undetermined multiplier, and we will get the final equation. So let me first discuss the how we calculate the combinatorial interpretation, and it is a symbolic thing. First we will use the box and ball method. It is a symbolic, and again I am just talking to you. Then you think that in place of ball, these are fermions, and in use of box, we are using the different energy levels and the quantum states. So for clarity and novelty, I am using GI. So it is up to you. There are many types of the interpretation. So suppose I am taking the 4 boxes and 3 balls. So how that 3 balls is distributed? Obeying the Pauli's exclusion principle. So generally we do all these things. Suppose there are one is G1 N1 particle is there. In G2 N2 particle is there. G3 N3 particles. Gi Ni particles are there. Or it's common idea like V and N. That is the thing. I will explain with the help of a ball. And we have to calculate the number of, suppose we are having 3 particles and 4 boxes. So you can put 1 particle in one box, another box, another box. So what is the unoccupied? I can write G minus n. Okay, because suppose there are 3 boxes, there are 4 boxes and 3 particles, and there is no restriction. Restriction is the Pauli exclusion. We cannot put 2 balls in one box. So G minus Ni, the number of available quantum states that are not occupied, that is G minus Ni. So if you see different types of book, there are many systems. So for example, here I am just showing indistinguishable particle, and this blue color is free. So again, it is an assumption. If you see different types of books, different types of research paper, different original paper, but this is just a crude method for biology students and other things. Or even I can write like that. Suppose this is E1 or E3, E2, maybe 3, maybe 4, maybe 5, like that. I can write that. The different types of quantum state. So just have to. Okay. Or I can write like that. One is 4 part. Like that. You see. So I can put one particle first in this place also. In second time I can put this particle here is also. In fourth place I can put, but everywhere only one thing. Or in fifth, fourth position. So 1, 2, 3. So, like that. So I can calculate the probability like that. Suppose there are 3 particles like that. Then 1 into 1 into 2 like that. So you can calculate this thing. But here what I am saying, suppose this is E1, E2, G1, G2, G3. So Pauli exclusion principle, only one particle in one box, but there are the different probabilities. First cases, first part is empty. In second cases, this part is empty. Third part, this is empty. Fourth cases, this is empty. So number of ways of selecting unoccupied objective. So 4 minus 3, and total number of particles is 4. 4 factorial. Ni is 3 particles, 4 minus 3. So if I solve it, 4 into 3 into 2 into 1, 24. 3 into 2, 6. So there is 4 combinations are possible. So before deriving any Bose-Einstein or Maxwell distribution, you have to solve the values of probability distribution, maximum probability like that. So number of ways of selecting unoccupied objective is G minus n, and there are n types of molecules, n types of particles. So what is the unoccupied is G minus n, but for total is Ni. We are just considering suppose the particles are distinguishable, but particles are indistinguishable. So therefore I have to write here n factorial, and total number of things is Gi. So our form, so number of ways arranging the n distribution G, G minus 1, then G minus 2, G minus n plus 1. So that is the very important thing is that, because if you do it correctly, then you will get the final equation. If you don't do it correctly, you will not get the final equation. So be careful while writing the combinations and other things. So on the basis of this simple combination, and it is up to you if you refer any research papers or any books, any video lecture. So I am just giving a simple combination for the mediocre student, the simple student, so that you can understand the things, and then accordingly you can do all these things. So, and because there are different types of waveforms, different states, 1, 2, 3, 4, like that. So therefore, I must use the formula that here is our final thing. Gi factorial Ni factorial G minus N. But there are various states, as I told you, G1, G2, G3, G4, and condition is that Gi is greater than Ni. So therefore, I will take the product of all the things, product of G1, G2, G3, G4, like that. So once I get this W, then I have to take the logarithm and Stirling approximation and other things. Do I make my point clear? Okay. Now I go for the second step. So again I am just, it is a repeating, because I have already given same thing in my previous lecture, whether it is Maxwell, Boltzmann, or even both Einstein. But just again it is a repetition. I will not discuss much more things. Two constants, the conservation of the particles, whatever these things, summation of Ni is the N1 plus N2, and it is equal to constant. And if I take the derivatives of this thing, it must be 0. Ultimately, similarly, these particles or the electrons having certain energy, you can write 0.10, or even directly you can write N1 associated with energy E1, N2 associated with energy N2, E2, like then E3. But again, if I take the summation of all these energies, also is a constant, and it not be Ni, it must be D. It must be summation of dE, energy, actually total energy. That means summation of dE Ni. I can write like that, Ni, or like that, or E1 minus E2, or even I can write like that, dN of N, E1 minus E0. And if I take the derivative of these things, it must also be 0. That is 0. So you just remember these things. And third is, last is the Lagrange's method. Again, I will not discuss the Lagrange's method. As I told you many times, that Stirling approximation I will not discuss, because the large number of particles, so you can use that log of x factorial x, natural log of x minus x. And we applied the Lagrange's method of undetermined multiplier, because in order to find out the maximum or minimum value of the function, that is the Lagrange's method of undetermined multiplier. Those want to go into details of the mathematical derivation of the Lagrange's method, or even Stirling approximation, I suggest you to refer the books of physical chemistry and refer the appendix site in order to get the complete information of that Lagrange's method. So I can write natural log of W minus, this is actually Lagrange's method of undetermined multiplier. Summation of Ni, summation of E by E0, that can be also written there. And then it is, of course, it must be there N. So I can write like natural log W minus alpha summation of Ni beta Gi Ni associated. It is up to you that you can write N related to, if you don't want to write the E0, in some books it is like that. So you can write simply, this is one undetermined multiplier, this is one undetermined multiplier, and this is associated with the energy, and this is a sphere with the total number of molecules. And again, I told you that I am taken this equation from the book of physical chemistry by G.M. Barrow, which is very similar. Any student can understand this. So then, if I, because my objective is that to get the maximum value. So d by dni, like that I can take like that. So if I take the derivative, so same thing, natural log of w minus alpha, that must be equal to 0. So that ni cancel. So I will get what is my final equation, d by d natural log of dni minus alpha minus beta I is to 0. So it up to this exactly similar to the Bose-Einstein and Fermi theorem. So I have to substitute this value of d natural log dni in this equation and get the final equation. That is the derivation. So let me now start the derivation. So now I will start the derivation. I need the board. So color is yellow color first. Okay. So W, first point, product of GI factorial. We should be very careful while writing this thing. Ni factorial GI minus Ni factorial. Okay. Now bear in mind that deliberately I am using capital N. Deliberately I am using, in some books, in place of capital N, you can write small n. So there is no hard and fast rules like that. So taking logarithm, natural log of probability is equal to, now when I take, so you can use summation, you can find summation. I do just write like that. So natural log of GI minus, because this is natural log of Ni, of course factorial, forgetting this thing. If I forget, please, natural log of GI minus Ni factorial. There is no problem. Now applying Stirling approximation. Nothing new for you. Stirling approximation. So natural log of, it's better to use yellow. Yellow. Or even white is also good. Let me see. So you know that natural log of n factorial n, natural log of n minus n, like that, whatever it is, or x like that. So it is, I can write what I can write, GI, which is also good, natural log of GI minus GI, isn't it? Then second, so n or I, you can whatever you like, natural log of Ni minus, because here is also minus, so I can write capital. I can use the summation term, so no problem. Then similarly this again minus gi minus ni natural log of gi minus ni. Again it is minus plus. So gi minus ni. So see very carefully. I can use the again red pen. Why? Because this gi, I just open the bracket, this ni plus this ni minus. So I will get again yellow color. I have to just so natural log of w summation. You can just have, if I have forgotten, you just write it. That is not a problem. Natural log of gi minus or ni or even n, you can write n, no problem. Ni minus gi natural log of gi. Just have to increase the board. Okay. Now you tell me, because you have already seen these things, because our, I can use the red color, because in the Lagrange's method d by dni natural log of w minus alpha minus beta er or ei is equal to 0. So I have to determine the value of dni natural log. So if you are a mathematics student, it will take only 1 minute, because if I differentiate it or the differentiation with respect to ni, and you know that gi is a constant, because suppose there are 4 energy levels, gi is constant always, but n is variable, n1, n2, n3, n4 like that. So if I take the differentiation of a constant, so it is always 0. It is always 0. And if you a math students, you know that if I just dy dx x natural log of x, so you know that x plus 1 whatever it is. But here actually I will get the final value. I will get the natural log of ni plus natural log of ni or dni total summation or like that. So what I can write dy dni natural log of w is equal to, but there are a large number of biology students are here, so I have to solve it differentiation by product, because there are 2 things. So there are 2 methods for biology students. Once you forget about the sign, you just differentiate it, first function into differentiation of second, plus second function into differentiation of first, again first function into differentiation of second. Or what you do is my suggestion. You can use any type of method. There is no restriction, there is no rule, but we need the final equation like that. So what I do for u, so if this part is 0, I think 0 again first. So summation you can write. So first function, forget about the minus, I think, right, by outside. So first function is ni. Second, d of dni, natural log of ni. Again, d by dx, natural log of x, 1 by x, isn't it? Plus. Second function, natural log of ni. Then again, differentiation of d by dni, 1. Forget about the minus and other things. So this is d by dni, that is eraser. So I can write like that. By ni. 1. So I can write like that. 1 plus natural log of 1 ni. Don't worry about the minus or plus. But if it is a minus, so it should be, I can write like that in the right side. So it is minus natural log of n minus 1. But I have not changed the bracket, or dni you can write like that, dni, so absolutely no problem. Then again there is a minus, so again I keep it outside. So here just if I take u is equal to g minus n, again for biology student, and v is equal to natural log of g minus n. So if I write dv, du upon dv, it must be minus dn, because this is a constant, this is a minus 1, and log x, so I can write dv dn minus 1 by dn, like that, gn, isn't it? Again for the biology student. So I can use the white color. It is very simple, it will take only 2 minutes. Directly you can write, but again for simplicity I am just doing all these things. Don't worry about the minus. So first function is g I minus ni. Okay. Then differentiation of second function, d by dni, it is g minus n. Remember, I can remove now this part, is actually not required now. So I just told you now, this is actually g is constant, so minus n, so it is the minus. So minus gn, I can write white color again, gn divided by gi, but here is a minus, because then again plus second function, natural log of gi minus n, d by dn, again first function ni, as I told you, it is minus 1, so it is again, it will be, here is minus. So gni log of gni minus 1. So what I will get finally, you follow this point, first function, second function into differentiation of first, g of ni. So there is no problem. Natural log vi like that, minus what is here. So here is 1. So now if I change this thing, so I will get minus 1 plus natural log of ni. Now here is minus plus 1. Here is also minus plus natural log of vi minus ni. So there is no problem. Last stage, gradually we are coming to that point. So we can write it again, yellow color. So this 1, then you can write the ni. So what I can write, e by dni, natural log of w is equal to, oh here is minus, I'm sorry, it is minus. So minus natural log of 9 plus natural log of vi minus ni, like that. What I can do this thing. So what I am getting, e by dni and w summation is equal to natural log of gi minus ni divided by ni. So I can give the final equation in the simplest method. Now I have to substitute this value in our, let me see that equation of Lagrange's method of undetermined multiplier. So you will get the final equation. So what is this Lagrange's method of undetermined multiplier? E by dni natural log of w minus alpha minus beta ei equal to 0. So I have to substitute the value of this from here. So I can write natural log of gi minus ni minus ni minus alpha minus beta equal to 0, or just the original natural log of gi minus is equal to alpha plus beta ei. Last step. So you know that if you remove that log, so I can use it red color, gi minus ni divided by ni is equal to exponential alpha or exponential e beta, you can also write of beta ei. Now listen very carefully. Can I write like that? Gi minus Ni minus 1 is equal to this thing is equal to exponential alpha plus beta Ei. Or our objective is just I'm getting these things. So Ni equal to or plus beta Ei if you want plus 1. Just give me plus 1. That is important. Where plus 1. So this is also you can write one form of that equation, but as I generally we write Ni in terms of Ni because the actual occupancy we want to calculate. So if I just reverse this equation, so Ni is equal to Gi, just your like Bose-Einstein exponential alpha, or even you can write plus 1, or even you can write like that exponential of alpha, exponential of beta. Yeah, there is no problem, but this is the actual correct form. Now this is the final equation of the Maxwell-Boltzmann series. But what is important here, as you know, that the value of alpha minus mu kbt and value of beta, as I have already told you, 1 divided by kbt. K is the Boltzmann constant. So if you substitute this value, it will get Ni equal to Gi. It is only for one electron system in one. So if I substitute this value, I'll get E minus mu kbt plus 1. Now this is actually chemical potential. It is temperature dependent. It is actually chemical potential. But I just, before I start my lecture, I just give you one instruction that this Fermi-Dirac equation can be converted into Maxwell-Boltzmann under certain conditions. That at very low density state and very high temperature, that part can be converted into Maxwell-Boltzmann. Second thing is that actually basically what we are doing? We are doing the Fermi distribution of electrons occupied in the different energy levels, and what should be the maximum energy. So it was observed that at absolute zero temperature, 0 K. I'll show you one graph at absolute 0 K, that chemical potential will be replaced by Fermi energy, ACR. If you study the nanomaterials analysis, so there is a Fermi energy and Fermi level, maximum energy level. I'll show you the actual picture. If you plot a graph between the distribution function, of course Fermi distribution function with respect to energy in terms of electron volt, maybe 1, 2, 3, 4 like that. So at absolute zero, it will maximum point, and that level is called the Fermi level, and that energy occupied maximum point is called the Fermi energy. Not that is a very additional thing is that. So that can be written like that. That can be also written like that. I can use yellow color. This last 5 minutes or 2 minutes. That Fermi F Fermi I can with respect to some energy, like the Fermi distribution, 1 divided by exponential E minus E Fermi F you can write like that, plus 1, and sometimes denominator values are numerator, because if this temperature density is very low, the N value is very less than this thing, and sometimes the chemical potential value is also very less as compared to the Fermi energy or the Boltzmann constant, then that can be converted into this thing. But the final equation is, again I am just, let me summarize this thing, because this is the last lecture of this series, of course. I will not again repeat the Maxwell, Boltzmann or Bose-Einstein or Fermi-Dirac, but the final equation you see that just like the same equation, alpha and beta in Bose-Einstein is -1, +1, and you know the Maxwell-Boltzmann distribution, Ni, Nz exponential E by kT, fraction of molecules. That is very important in spectroscopy, superconductivity, and everywhere, nuclear physics, astrophysics, and other things. So the last part I will show that graph. It is available in the, but if you just see the books, they just ask the derive the Fermi-Dirac equation. So let me just go to the all original side. Which one? Yes. Just I am opening the first part so that you can understand this thing. Yes. You see. Again, this is Ni by Gi1 divided by exponential alpha beta Ei plus 1, and the values of minus, and so I can get this value. But now I will show you that Fermi energy. One diagram I have taken from the literature. So just I remove that chemical potential, which is temperature dependent function. If I change the temperature, that curve is also changed. If it is 0, that is the maximum point. I will show that the last part of this lecture. I hope that you have enjoyed this series, and it is very simple. Yes. So sometimes a small question may be asked that how that Fermi-Dirac distribution approaches Maxwell-Boltzmann distribution in the limit of high temperature and low particle density. This is our final formula. Same thing. So of course, if the particle density is enough, because it depends upon the particle density, you know. So that 1 divided by exponential E kT1 is very less than 1. So if it is less than 1, so I can write this, that it is now. So this exponential part is greater than 1. So I can write by this formula. And if the temperature is very high, so the energy is greater than the chemical potential. That energy is greater than the chemical potential. And occupancy probability is very low, making the 1 in the denominator. So it is just converted into Maxwell-Boltzmann. It is just a very short type of the question, that how and what is the relationship between Maxwell-Boltzmann and Bose-Einstein and Fermi. And the last part is that if you do research, or if you go some good book or research paper, original research paper, you get all such type of the information. But for a M.Sc student, just very simple thing, that what is Fermi energy, because when you study the material science, nanoparticles, Fermi level, superconductivity, semiconductor, that is very important, valence band, conduction band, electron occupancy, transitions, and other things. So if I plot a graph between this Fermi distribution with respect to Fermi energy, so this at absolute 0, the value of the chemical potential is defined as the Fermi energy. So you see this. Then this is one T1, this is T2, this is T3, but this is the highest point. So this is called the Fermi energy. This point is Fermi energy. And another thing is that how I remove this thing. Fermi level energy level is that energy level where there is a maximum probability of finding electrons at the absolute zero. You see, if it is zero and the probability distribution, so where we get the maximum point? That point. So at absolute zero, the value of chemical potential, because in our formula, you know, exponential E, the related energy, minus E in place of mu, we write Fermi. Where when the temperature is absolute zero. That is the Fermi energy. And that Fermi energy, we are getting the maximum probability of finding electron at absolute zero temperature. That is called the Fermi level. So, thank you for patient hearing. And let me summarize that this is the last distribution part. And thank you part. And if you plot a graph between Fermi energy and the distribution, the same thing. It's the same representation. If you increase the effect of temperature and other things. So I think I have completed your course content. Maxwell-Boltzmann, Bose-Einstein, and Fermi-Dirac. My next lecture will be the application of Bose-Einstein statistics, because one of the most important applications is the derivation of the Planck's equation, Planck back body radiation from the. There are many other applications. So thank you, and thank you the Pandit Ravi Shankar Shukla University Mathematics Department, particularly Professor Balwant Thakur, Dr. Dipti, Mr. Indra Kumar, for providing me this very good lecture capturing facilities. I am also grateful to my research scholar Abhishek Katendra for recording this system, and he has prepared large number of graphs and some equations of that thing. I hope you have enjoyed this thing. Thank you very much.